This theory lesson on RTDs will involve lots of circuit diagrams. Sorry about that. Shown on the right side of this slide is a simple circuit for measuring resistance, but there's a flaw in this circuit that dooms it to a grisly failure. You need a lead wire to attach the RTD to an embedded circuit, and that lead wire has a resistance that's not accounted for in the specs. Oops! Let's do the math. The RTD sensor has a 100 ohm resistance at 0 degrees C. The slope of the calibration curve is 0.385 ohms per degree C. Typical lead wire resistance is somewhere between 1 and 10 ohms. We'll be conservative, we'll just use 1 ohm. The problem is that even adding 1 ohm to the circuit resistance throws off your temperature reading. Simply divide the 1 ohm by the slope of 0.385 ohms per degree C, and you just added a fictional 2.6 degrees C to your temperature reading. When in doubt, construct a Wheatstone bridge. Let's try it here. Shown in the upper right corner of the slide is our first attempt. The 3 fixed resistors in the bridge have a much smaller TCR, or thermal coefficient of resistance, than the platinum RTD, but still not 0. Unfortunately, putting them next to the RTD means that the resistors will see the same up and down temperature excursion as the RTD, and so they'll no longer be fixed resistors. I got it. Let's add long lengths of wiring to the 3 fixed resistors and mount them remotely at a stable temperature. But now we're going around in circles. By adding lead length, we have recreated the problem we had in the last slide. Stay tuned, folks. When in doubt, stick to your Wheatstone bridge, but use only 3 wires. Well, let's try it here. Shown in the right side of the slide is our next attempt. Make sure that lead wires A and B are of equal length and the same type of metallurgy. Because wires A and B are on opposite sides of the Wheatstone bridge, their resistances cancel. Lead wire C is dead-ended, so it carries no current. But now we just lost our linear relationship between temperature and resistance. Stay tuned. When in doubt, keep grinding through the calculations. Let's try it here. Shown in the top of the slide is our Wheatstone bridge with resistance values assigned. We set R1 equals R2 so that they conveniently drop out of the calculations. Also, if the RTD element is located some distance from the bridge in a 3-wire configuration, the equal and fixed lead wire resistances, RA and RB, will be buried inside the total resistance R for the RTD and R3 respectively. Let's keep it simple at first and assume these resistances are very small and assumed 0. By applying the equation for the voltages in a Wheatstone bridge to our situation, we get that V0 equals V times R3 over R3 plus R minus V over 2. Then we can solve for R, the resistance of our RTD, as R equals R3 times 1 over V0 over V plus a half minus 1. Almost done. Almost done, but not quite. When in doubt, assume resistances are 0, but go back and add them in at the end. Shown in the top of the slide is our trusty Wheatstone bridge, but this time with equal but non-zero values for RA and RB. Now, we substitute the sum of R plus RA for R and R3 plus RA for R3. We get a clean equation this time for R. Now, R equals R3 plus RA times 1 over V naught over V plus a half minus 1 minus RA. We seem done, right? Not quite. We're only done if RA is known and constant for all installations. In real instrument panels, technicians use all kinds of lead wire lengths, whatever is needed to get the system wired. So your perfect calculation of R will be thrown off slightly. And if you need the best accuracy an RTD system has to offer, you should purchase a 4-wire RTD. Calculations in this case are left to the reader. Sorry. When in doubt, assume linearity. But in reality, RTDs are not perfectly linear. Here's a plot of temperature error for assumed linearity versus temperature for the full temperature range of the RTD. You have negative errors below roughly 200 degrees C and positive errors above that reading. We need a way to straighten out the mess, so to speak. When in doubt, postulate a set of polynomial curves. Here's some real-life polynomial curves that can straighten out the mess. In order to linearize the RTD, we have to calibrate it to a fixed and more accurate temperature source at several points along the curve. For temperatures below 0 degrees C, we use this third-order polynomial, and we must calibrate the RTD at 3 points to obtain values for the constants A, B, and C. For temperatures above 0 degrees C, we use this second-order polynomial, and we must calibrate the RTD at 2 points to obtain values for the constants A and B. Now that we've put all our doubts to rest, it's time to go shopping online for an RTD. This is the V-shaped IC we showed briefly in the previous video. It meets the specs of IEC 60751, and it gets to 90% of its final temperature reading within 2 seconds if you put it in the airstream it is measuring. Of course, I'm not sure how you do that when the chip's going to be mounted on a board. So hence, in reality, I'm sure the chip's going to be slower than what's shown in the spec sheet. Let's select the PTS0603 chip we showed before. It has a resistance of 100 ohms at 0 degrees C. The TRC, or the temperature coefficient, is 0.385 ohms per degree C, shown here in the spec sheet as 3,850 parts per million per degrees K. It has a temperature operating range of minus 55 C to 155 C. It's narrower than max for an RTD, but it's still more enough for the board where I'll mount the chip. Note also the tiny amount of long-term drift quantified under the long-term drift stability. Oh, wait a minute. What are those other ICs doing with their resistances other than 100 ohms? Here's PTS 0805 coming in with 100 ohms and 500 ohms of resistance. And PTS 1206 comes in with 1,000 ohms resistance. I thought you said that DIN IEC 60751 specifies a resistance of exactly 100 ohms. Yeah, but here's the deal. Who says that all sensor manufacturers follow one standard? In the sensor industry, people also sell 500 ohms and 1,000 ohms RTDs. Recall our assumption 4 slides back that the lead wire resistance in a 3-wire RTD had to be small enough that they wouldn't affect accuracy too much. Well, if you jack up the nominal RTD resistance from 100 ohms to 500 ohms or even 1,000 ohms, your lead wire resistances are comparatively even smaller. Therefore, your system accuracy for an RTD with 3 wires and either 500 ohms or 1,000 ohms improves accordingly relative to the system with 100 ohms. Let's recap. We discussed the core technology and the calibration equations that govern RTDs. Now let's discuss the accuracy range and typical applications for thermocouples.